Hello, my name is Jendrik Seipp and I'm going to talk about online saturated cost partitioning for classical planning. So the setting that we're concerned with is optimal classical planning, and we're using an A-star search with an admissible heuristic to find optimal solutions. Since usually one heuristic is not enough, we use multiple heuristics, and here we focus exclusively on abstraction heuristics. And we use cost partitioning to combine their estimates. In particular, we're using saturated cost partitioning to do this. So what's this talk about? So one of the strongest planners based on saturated cost partitioning has this kind of runtime behavior. So we see here the time that it runs in seconds, going from 1 second to 1000 seconds. And we see here the number of tasks that it solves. And what becomes clear is that it does nothing, or it solves no tasks for 1000 seconds. And this is because it has such a long precomputation phase. And in this talk, I'll show you how to reduce this precomputation phase without reducing the number of solved tasks. But let's start with some background first. So here we have two example abstractions, 1 and 2. And let me explain what these mean. So here we have an abstract state that combines two concrete states, S1 and S2. We have several operators in different colors here that have different costs. For example, this operator costs 4, the blue operator costs also 4, and those here cost 1. And we have a goal state that is doubly circled. And so if we have these two abstractions and we want to find out what is the goal distance of the concrete state S2, what we can do is we can find out which state it belongs to, so this abstract state, and then compute the abstract goal distance from this state to the nearest goal, which is 4 plus 1 in this example. If we do this for both abstractions, we get an estimate of 5 here and an estimate of 4 here. And what we can do to obtain a combined estimate is to maximize over it. But this only selects for each state the heuristic that is more informative for this state. What we really want to do is actually combine the heuristics. And we use cost partitioning for this task. And cost partitioning works by splitting the action costs among the heuristics, so that the sum of costs doesn't exceed the original cost. So an example for this would be that we assign this operator a cost of 2 here, and in this abstraction a cost of 1. 2 plus 1 is still not 4, so we're good for this. Also the others don't exceed their original cost. And if we split these costs among these two abstractions, then we can actually sum the heuristic estimates from these two abstractions. So what we get is 2 plus 1 is 3, and here for S2 we have 3, so a total estimate of 6, which is already better than the maximum. But the question is, how do we obtain such a cost partitioning? And one of the strongest methods for this is saturated cost partitioning. And it works by ordering the heuristics, and then for each heuristic it uses only the minimum costs that preserve all estimates of this heuristic under the remaining cost function. And then we can use the remaining costs for subsequent heuristics. So in this example, we say we start with the first abstraction and we compute all abstract goal distances and see that we can actually reduce the costs for this operator here to 1 without affecting any goal distance. And we can also reduce the cost of this operator to 0 because it's a self-loop. So we do that, and then we can use the remaining costs in this abstraction. So this is what we have here. And now we see that we don't even need the costs for this operator here. And then we can compute the goal distances again and sum the estimates and obtain an estimate of 8, which is better than the maximum and also the other example that we saw. And in saturated cost partitioning, the order is very important. So when we say we consider the first heuristic first and then the second, we get an estimate of 8. If we do it the other way around, we only get an estimate of 7 for state S2. And what we usually do to avoid this kind of situation is we use multiple orders, compute the saturated cost partitionings for them, and then we maximize over the estimates. So this is what is depicted here. And the best method discovered so far for obtaining multiple orders is diversifying the set of orders offline before the search. So this works by sampling 1000 states, and then we start with an empty set of orders, and until a fixed time limit is reached, which is 1000 in the example I gave earlier, we compute an order for a new sample and store this order if the sample profits from it. So that means if the order obtains a higher saturated cost partitioning estimate for this state, for this sample, than all other orders before it. And this leads to this kind of behavior. So we do this sampling and order computation and saturated cost partitioning computation for 1000 seconds. We store all these orders, and then we actually run the A* search. But this is obviously not desirable. What we want is we want to start early and use the available information early and already solve tasks. And we can do this if we compute saturated cost partitioning for each state evaluated during search, and this has already been done. But it has the drawback that it's very slow to evaluate, because computing saturated cost partitionings for each state is too slow, slows down the heuristic too much, and we can see that we solve problems quickly, but we don't reach the high coverage of the offline diversification. And what is interesting is we can actually combine these two approaches by diversifying the set of orders online during the search. And this is what we do in this paper. And if we do this, we can actually see the result of the whole work here in this picture quite nicely. We start solving tasks very quickly. So even in 1 second, we already solve 400 tasks. And then we gradually improve our coverage until we actually reach the coverage that is obtained by offline diversification. Okay, so let me explain how we actually do this online diversification. So what we change is we use the function that actually computes the heuristic for a state S. And usually this function just returns the maximum over a fixed set of orders for S. But for some states, and until the time limit is reached, so we need a time limit for this approach as well, we compute an order for this state and store it if it benefits from it. So this is pretty similar to the offline diversification. But we only select from the states, from the set of evaluated states. So to compare this more directly, we have here the offline diversification and the online diversification. And in offline diversification, we compute orders for samples for a fixed amount of t seconds, 1000 for example. And in contrast, in the online version, we compute orders for a subset of evaluated states instead of samples for at most t seconds. So we don't have to use all of the 1000 seconds. And what's more, in the offline diversification, we store an order if one of 1000 samples profits from it. And here in the online version, we only need to evaluate a single evaluated state and obtain the total coverage that is the same as the offline version. That leaves the question, how do we select the states that we compute orders for? And we try three different methods for this. The first is the simplest. We just choose a fixed interval and then we compute an order for every 10th state, every 100th state, or so on. The second one is based on the concept of novelty. So here we compute an order if a state is the first state that we see that makes a given atom, or a new atom true, or a pair of atoms. The third one stems from the Bellman inequality and has actually been used by Eifler and Fickert for deciding when to improve heuristics. And the Bellman equation looks like this. It says that the heuristic value for a state S must be at least as high as the heuristic value of one of its successors plus the cost of going from S to this successor. And this, if this inequality is violated, we know that the heuristic makes an error, because we know that this distance must be at least as high as h of t, and there can't be and we can only reach the goal from S going over t if S is not a goal state. So if this doesn't hold, then the heuristic is too low for S, and it might be a good idea to compute an order for S. So how do these fare in practice? We see that the Bellman variant solves 1145 tasks, which is a little less than the other variants, which perform more or less the same. And the best variant uses an interval of 10,000 states, which is what we use in all the other experiments. So let's compare the offline and online diversification in this graph. So here we see different diversification times. So if we only diversify for 1 second here, or for 1000 seconds, and the number of tasks that this resulting algorithm solves then. We see that for the extreme cases of just 1 second of diversification or more than 1000 seconds, the online version solves more tasks, but for the other choices, they are more or less the same. But what's really different is if we evaluate how long they run, obviously. So here we see the same diversification time, but this time we evaluate the time score that was used in IPC 2018. And we see that the time score for the online variant stays more or less the same, regardless of the diversification time, but the time score drastically decreases over time for the offline variant, because it just uses such a long precomputation phase. So if we look at what we have to do before the A-star search can start, we see that we have to build the abstractions, obviously, for example, the Cartesian abstractions and symbolic PDBs. And to interleave this with the A-star search, we can use online refinement, as has been done in the literature for both Cartesian abstractions and symbolic PDBs. And then we have to compute orders and cost partitionings, for example, for saturated cost partitioning. And we saw already in the literature that we can use the Bellman inequality, or in this talk that we can use the novelty criterion or a fixed interval for this. And a third thing that we need to do before the A-star search can start is to choose which abstractions to build. So, for example, which patterns to use for a pattern database heuristic. And at least I don't know any work that has considered this so far, so it would be interesting to see how to interleave this part of the precomputation with A-star search, and also how to combine all these three things together and inside and during an A-star search. So to wrap up, we have seen that offline diversification suffers from long precomputation phase, and it has to use samples and can't work on really evaluated states. On the other hand, it has very fast evaluations and therefore high coverage. The online computation needs no precomputation and can work on the states that are evaluated, but it suffers from this low evaluation and has low coverage as a result. The online diversification combines the advantages of the other two methods in that it needs no precomputation, it can work on the states that are really evaluated, and it obtains fast evaluations and therefore high coverage. Thank you.